In today's lecture, I'm going to talk about the subdifferential chain rule. The goal of the lecture is to derive a subdifferential formula for the composition of a convex function and an R-phi mapping. So let B from Rn to Rp be an R-phi mapping. That means B of x can be represented as Ax plus B. Here x is in Rn, where A is a P by N matrix, and B is an element of Rp. Now let F from Rp to the extended real line be a convex function. Then the composition of F and B is a function from Rn to the extended real line. And as we know earlier that this composition is a convex function. So a natural question is as follows. If we fix any x bar in Rn, how can we compute the subdifferential of the composition of F and B at x bar? Okay, so in this lecture, we're going to use the normal cone intersection rule in order to derive such a formula. And it turns out that this subdifferential depends on the subdifferential of the function f and also the matrix A. Okay, and let me start with a very useful lemma that is used in the proof of the main result. This is the lemma. Let B from Rn to Rp be the R-phi mapping defined earlier. Then for any x bar, y bar in the graph of the function, the mapping B, we have the following. The normal cone to the graph of the function of the mapping at x bar, y bar can be represented as follows. It is the set of all order pair UV in Rn times Rp such that U is equal to minus A transpose times V. Okay, so note that if B is an R-phi mapping, then the graph of B is always an R-phi set, and in particular it is a convex set. So this formula represents the normal cone to the graph of B at any point x bar, y bar. Note that over here, because x bar, y bar is in the graph of B, y bar is always equal to B of x bar. Okay, so let me go ahead and use the definition of the normal cone to convex sets in order to prove this useful formula. So fix any u and v in the normal cone to the graph of b at x bar, y bar. By the definition, the inner product of u and x minus x bar plus the inner product of v and y minus y bar is always less than or equal to 0 for all x and y in the graph of B. Now we have the following. The inner product of u and x minus x bar plus the inner product of v and bx minus bx bar is equal to the inner product of u and x minus x bar plus the inner product of v and ax minus ax bar. Note that this is true because b of x is equal to ax plus b and bx bar is equal to ax bar plus b. Therefore, bx minus bx bar is equal to ax plus b minus ax bar minus b, and we end up having this formula. Now we continue the calculation as follows. This is equal to the inner product of u and x minus x bar plus the inner product of v and a times x minus x bar. Okay? This can be written as follows. This is the inner product of u and x minus x bar plus, note that this is equal to the following. The inner product of the transpose of a times v and x minus x bar. This is a very familiar formula from linear algebra. So then we have the following. This is the same as the inner product of u plus the transpose of a times v x minus x bar. Okay? Using this formula, we have the following. Then uv belongs to the normal cone to the graph of the function b at x bar, y bar if and only if the following condition is satisfied. The inner product of u plus a transpose times v x minus x bar is less than or equal to 0 for all x in Rn. Okay? Note that this condition is equivalent to the following. U plus A transpose times V y is equal to is less than or equal to 0 for all y in Rn. Now, if this is true for an element y, this is also true for minus y. So this is equivalent to the inner product of u plus the transpose of a times v, y is equal to 0 for all y in Rn. Okay? And this is true again if and only if the sum of U plus the product of A transpose and V is equal to 0. Or equivalently, U is equal to minus the product of A transpose and V. Okay? So from this we have the following. UV is in this normal cone if and only if U is equal to minus transpose of A times V. And therefore we have completed the proof of the lemma. Note that in the proof of the previous lemma we used the following useful fact. The inner product of W and Y is equal to 0 for all Y in Rn if and only if W is equal to 0. This fact is very easy to see. So if W is equal to 0, then we can see easily that the inner product of W and Y is equal to 0 for any Y in Rn. Now, if this is true, then we can choose any Y in Rn and we have that the inner product of W and Y is equal to 0. So, in particular, we can choose Y to be W. Then we have the following. The inner product of W and itself is equal to 0. This implies the norm of W square is equal to 0, and so W has to be 0. Okay? Now, let me continue with deriving an important proposition for the main result. Let B from Rn to Rp be an R5 mapping given by B of x is equal to Ax plus B, where A is a P by N matrix. And B is an element in Rp. Now let F from Rp to the extended real line be a convex function we fix any x bar in Rn such that the element y bar, which is B of x bar, belongs to the domain of the function f. Okay, with this assumption, x bar belongs to the domain of the composition of f and b. Okay, and then we have the following. Then the subdifferential of the composition of f and b at x bar always contains the following set. It is the product of A transpose and all vectors in the subdifferential of the function f at y bar. So this is just the union of all elements of the form A transpose times V, where V belongs to the subdifferential of the function f at y bar. Okay? So let me go ahead and give the detailed proof of this proposition. We fix any u in the in this set A transpose of the subdifferential of f at y bar. Our goal is to show that u belongs to the set on the left. Then, by the definition, u has the following representation: is the product of A transpose times V, where V belongs to the subdifferential of f at y bar. We have the following. For any x in Rn, the inner product of u and x minus x bar is equal to the inner product of the transpose of A times V x minus x bar. Okay, this is equal to the inner product of V and AX minus AX bar. As we know earlier, by the definition of the R5 mapping B, we have the following. This is the same as the inner product of V and BX minus BX bar. Again, this is true because B of x is actually AX plus B, and B of x bar is equal to AX bar plus B. Okay. Now, at this point, we are going to use the definition of the subdifferential of the function f at y bar. By the definition, V belongs to the subdifferential of f at y bar. If and only if this is true, the inner product of V and y minus y bar is less than or equal to f of y minus f of y bar for all y in Rp. So, in particular, here if we denote this by y, and we know that this is y bar, then the inner product of V and y minus y bar is always less than or equal to the following: f of y minus f of y bar. So it's f of bx minus f of b of x bar. So by definition, this is just the same as the composition of f and b of x minus the composition of f and b of x bar. Okay. To summarize, we see the following: the inner product of u and x minus x bar is always less than or equal to the composition of f and b of x minus the composition of f and b of x bar, and this is true for all x in Rn. By the definition of the subdifferential, we have the following. Therefore, this element u belongs to the subdifferential of the composition of f and b at x bar. Okay, so we have completed the proof of the proposition. Now we are ready to derive the main result of the lecture. As we know, B is an R5 mapping that goes from Rn to Rp. And f is a convex function from Rp to the extended real line. In this theorem, we're going to show that if the domain of the function f intersects the range of the function b significantly, then we actually have the equality in the previous proposition. So what does it mean by the domain of f intersects the range of b significantly? It means the following: the relative interior of the domain of f intersects the range of the function b, that means b of Rn. Okay, so if this intersection is non-empty, then we always have the following subdifferential sum rule. The subdifferential of the composition of f and b at x bar is equal to the transpose of A of the subdifferential of f at y bar. Over here, we use the same setting as the previous proposition. So let me go ahead and write out the theorem and give the detailed proof. Consider the setting of the previous proposition we suppose the following. Suppose that the relative interior of the domain of the function f intersects the range of the function b. This condition also means the following: the range of b contains some point of the relative interior of the domain of the function f. Note that this condition is always satisfied if f is a real value function. That means f of x is a real number for all x in Rn. Then we have the following subdifferential chain rule. The subdifferential of the composition of f and b at x bar is equal to A transpose of the subdifferential of f at y bar. Over here, as we see earlier, y bar is equal to b of x bar. Okay. Now, in the previous proposition, we already proved that this inclusion is always satisfied. And note that this inclusion doesn't require this assumption. Now, under this assumption, we will show that we actually have this inclusion and therefore obtain this nice equality. Okay, so let me go ahead and give the detailed proof of the main theorem of the section. Now, fix any u in the subdifferential of the composition of f and b at x bar. Our goal is to show that u belongs to the set on the right hand side. Now, by the definition, the inner product of u and x minus x bar is always less than or equal to the composition of f and b of x minus the composition of f and b of x bar, which is the same as f of bx minus f of bx bar, and this is true for all x in Rn. Okay, in order to show that u belongs to the right hand side of the formula, we are going to use a geometric approach. In order to accomplish that, we define the following sets. Omega 1 is the Cartesian product of the graph of B and R, and omega 2 is the Cartesian product of Rn and the AP graph of F. Note that both of these sets belong to the Cartesian product Rn times Rp times R. Okay, let us divide the proof into several steps. In the first step, we will show that the relative interior of omega 1 intersects the relative interior of omega 2. Okay, and then after using this assumption, we can proceed by using the normal cone intersection rule to complete the proof. So under the assumption made, let us show that this intersection is non-empty. Okay, in order to do so, let's look at the relative interior of omega 1. This is the relative interior of the graph of B times R. The relative interior of this Cartesian product is the relative interior of the first set times the relative interior of the second set. Note that B here is an R5 mapping. We can always see that the graph of B is always an R5 set. Now, if we have an R5 set omega, then we have the following. We can see that half of omega is equal to the relative interior of omega and is equal to the whole set omega. So this is a very important fact that we can derive easily from the definition. So here we have the relative interior of the graph of B times the relative interior of R, but this is nothing but graph of B times R. Okay. Now let's look at the relative interior of omega 2. The relative interior of omega 2 is equal to the relative interior of Rn times the AP graph of F. Okay. Again, this is the same as the relative interior of Rn times the relative interior of AP graph of F. Okay. Now the relative interior of Rn is the whole space Rn times the relative interior of the AP graph of F. Now finally, in order to continue, we apply a well-known formula for the relative interior of the AP graph of a convex function derived earlier. So this is the set of all x, y, lambda in Rn times Rp times R, such that y belongs to the relative interior of the domain of F, and lambda is strictly greater than f of y. Over here, x is any element of Rn. Okay, so now under the assumption made, let's go ahead and show that this is non-empty. Indeed, under the assumption made, we have the following. This intersection is non-empty. So we can fix an element y0 in this intersection. Fix y0 in the intersection. So y0 belongs to the relative interior of the domain of the function f. And at the same time, y0 is equal to b of x0, because y0 is in the range of the function b for some y0 in Rn. Okay? Then we can form, for example, the following element. x0, y0, and the third component is f of y0 plus 1. Okay? So this is lambda. This element is in Rn. This element is in the relative interior of the domain of the function f. Okay? So then, first of all, by the first formula for the relative interior of omega 1 is just the graph of b times r. Okay? Here, y0 is equal to b of x0. So this order pair belongs to the graph of b. And this is any real number. So this element belongs to the relative interior of omega 1. Now, if we look at the formula for the relative interior of omega 2, here x0 is any element in Rn. This element lambda satisfies the following condition. Lambda is strictly greater than f of y0. This is true because lambda is just f of y0 plus 1, while the y0 belongs to the relative interior of the domain of the function f. Therefore, this element belongs to the relative interior of omega 2. So we have proved that the intersection of the relative interior for omega 1 and the relative interior of omega 2 is non-empty. By the way, those sets are convex sets in Rn times Rp times R.